Chapter 5, Network Cabling, Part 2. In our first half of our lecture, we looked at all things copper, right? Copper cabling, Cat5, Cat6, whatnot. In this second half, we're going to be comparing that to fiber optic cable. So what actually is a fiber optic cable? I mean, we hear the term quite a bit. It's really just a little piece of glass. It's a little glass fiber, slightly larger than a hair, in which light is beamed through it, right? And the source of the light for our purposes is usually from a laser or an LED. And this little piece of fiber is surrounded in a piece of plastic. And there's your cable. We see fiber optics all the time, though, even not only on data stuff. I have a Halloween decoration that's a cat head, and it's got these whiskers that light up. And you plug it in, the end of the whiskers light up. Well, those whiskers are fiber optic cables without that protective cladding. This is the same thing, only instead of going 6 inches or 8 inches, this light is going for a considerable distance, in some cases, miles. A lot of times, along with the fiber optics, you're going to see this little fuzz in there, and that's just it's a little buffer to protect the cable, to keep it from, give it a little bit of resistance. Now, this cable is pretty delicate, right? Compared to copper, I don't want to be stomping on this. I don't want to be twisting it too hard. I mean, if I twist a length of fiber optic cable in a circle less than about 4 inches, I'm going to break it. So it certainly has some disadvantages going to it. Not even begin to the fact that it's like really, really expensive, at least compared to copper. So why would we even use this? Why is fiber optic cable a thing? And in data centers, it is really a thing. Well, for one thing, it can support really high throughputs, right? We see this a lot in storage area networks. There's a whole storage protocol called Fiber Channel that it's a protocol, and it's also the physical layer, which is fiber optic cable, meant for moving large sets of data very, very quickly. Remember back on how copper had this crosstalk thing going on, our whole induction constant we had going, electrical signal passing through a piece of copper gives off a magnetic field, and if that field comes in contact with another piece of copper, it'll induce noise. Well, fiber optic is light. Right? There is no crosstalk. It's not going to be interfered by anything. So it's very highly noise resistant. I can run fiber optic in places I can't run copper. I can send this to right along electrical conduit if I wanted to, assuming code let me do it, and I don't have to worry about the crosstalk coming from it. It also has security. It is actually possible to listen in to a copper cable, right? That magnetic field that gets beamed out around it. If you have the right equipment, you can get close to that cable, stick an antenna out there, and measure that magnetic field. From there, you can turn around and recreate the actual signal that was used to cause it. In high security environments, that's actually a real concern. Well, again, fiber optic cable, light, not electricity. There's no crosstalk. There's no emanations. So it's very hard to hack into. And if someone tries to get to the cable to try to cut it, they'll just break it. Remember that Cat5, Ethernet over Cat5 anyway, Cat6 had a effective distance of 100 meters, 385 feet? Well, that was because of the resistance inherent to the copper cabling. Fiber has much less resistance because, again, this is light, right? And we'll see here in a minute there's a couple different kinds of fiber optic cable, and there are some types that can carry signals for kilometers. Now, it does have a few drawbacks. I mean, it's not perfect, namely cost, right? This can be pretty expensive, especially if you're doing any large amounts of it. I've seen the connectors alone be like $8 to $10 a piece. Compared to pennies for an RJ45 connector. So there is a cost there. And it requires not only special equipment to be able to splice it and terminate it and all that, but a special skill set. It's not easy. I had to do that when I was working for the government, and I burned through a lot of connectors, courtesy of your tax dollars, And personally, I was never really that great at it, right? We had some people that were awesome at it. So it does require a special skill set and practice to maintain. Notice our lengths here. We talked about this other stuff already. We can have segment lengths, again, depending on the type of cable, anywhere from 150 to 40,000 meters. That's a pretty long cable run. This is where we can connect elements of like a metropolitan area network together. And we totally do this. You see it all the time. You'll see a company or an organization have a data center in one side of the city and maybe have a standby site on the other side of the city. It's not necessarily ideal since you're in the same city, but a lot of governments still do this, and large corporations. Well, what they do is they actually run a length of copper through public conduit from one building to the other, and the extreme length of fiber allows us to do that. So we have two types of fiber we need to think about. We have single mode fiber and multi-mode fiber. Single mode fiber, now this is the stuff that goes long hauled, right? This is actually a really, really narrow core. That little copper hair is only 8 to 10 microns in diameter. So we're talking about a really narrow cable. And it's got to have some cost associated with that. It really does. Now, again, this can go for miles. The signal doesn't disperse, it doesn't degrade, but it's specific for long-haul connections. Very rarely will you see this used inside a data center, right? It's extremely expensive. But for your long-haul connections, as we point out here, even the internet backbone is based off of this. If you have to go any distance whatsoever, single mode's the way to go. And the reason it's called single mode is that it's only a single, it's basically a simplex. It's only a single, or excuse me, it's baseband. Only a single transmission is going through it at a time. Contrast that to multi-mode fiber. Now this is a much thicker fiber, right? The core on this thing is 50 to 62.5 microns. The most common one I've seen is 62.5. If that's getting a little bit bigger, you can actually see it, right? You can hold it up. At my age, I need glasses to see it, but you can see it. You can work with it. Look at the size at single mode fiber, 8 to 10 microns. Same idea, laser or LED beams light down through here. However, it does have greater signal attenuation than single mode fiber. That thicker core, the fact that we have multiple signals going down it at one time, means that it doesn't run as far. But for data center uses, it's fine, right? It can still take care of any of the needs I have in my data center, or for my storage area network, or all of that. And in high security environments, I've actually seen fiber all the way to the desktop throughout a 40,000 square foot building. So this totally can be done. Well, if I have a fiber optic cable, I got to connect it somehow, right? And I have different kinds of connectors based on whether it's single mode or multi-mode. Most of my connectors, and what I'm looking at right here is something called an ST connector. Attaches right to the very end, and it actually twists on. And that little ferrule you see right there in the middle, that is a material that is adhered to that little copper hair inside the cable. Sometimes it's done by crimping it on, sometimes it's done by gluing it on. But at any rate, if you beam light through this cable, you'll see the light appear out of the end of that little ferrule. It's delicate, so you have put this old plastic cap on the end to protect it in the event it's not plugged in. And what do I plug it into? Well, I got to have something that can take fiber. And in the context of this class, networking, we're going to be plugging it into networking devices like switches. Well, you're not going to see many switches that are all fiber, although they are available. Most commonly, though, what we're going to see in the form of SFP modules, also known as GBICs, right? It's a little device like this. And right here in the end is where I would plug my fiber into. And then I take that GBIC and I would stick it into a GBIC slot, let's say on a switch. And now my copper switch can talk fiber. This could be a router. Same idea. As long as I have a GBIC slot, I can fit into it. My pluggable module goes right in, and I can use fiber on my environment. Very commonly, the backbone in our networks is fiber. So we might use GBICs connect switch to switch to switch to switch, and we connect our workstations using copper. It might be useful if you need to actually test if your fiber is working, right? I wonder how we do that. Well, the easiest way is to put a laser on it and beam it through. You can put this little device on the far end if you want. It's called a loopback connector. Because your fiber cables, you always have two cables. All right, so if this is my fiber optic cable, I got one for send and one for receive. And very commonly, these are wrapped in the same cladding. So when I pull the insulation away, I'm going to see the two little fiber hairs here, and I would have to terminate each one of those separately. Right? What my loopback connector does, let's put the same thing over here. Here's my fiber connection. There's my connector. And this little device, what it does is it connects the send line from one side around into the receive side of the other. So when I shine a light in this side, that light goes belting off down this fiber cable, out this side, gets looped back around, and all the way back through, and comes out this end. Right? That way I can tell if my fiber is broken anywhere along the line. This isn't the only tool I have for troubleshooting, but it's one of my tools. Remember on copper, we talked about our Ethernet standards for it, and we talked about things like 10 base T and 100 base T and 1,000 base T and all that. Well, we have the same kind of standard for fiber. And we have different speeds. Now, we don't see 10 megabit fiber, so that's like 10 megabits like such a 90s thing. But we do see 100 megabit base fiber, right? It'll go across multi-mode fiber. And it would support fast Ethernet. And look what the standard would be, 100 base FX. So whereas 100 base T was our standard for going across copper, to T meaning twisted pair, 100 base FX is the same thing, 100 megabits, baseband transmission going across fiber. And we see the same ratings up through here. And all of these, LX, SX, SR, SW, they all mean fiber. Notice my ranges, my maximum distances over here. Right? When I start getting into this 10 gigabit stuff, look at this, 40,000 meters across single mode fiber. Going at 10 gig. That's a pretty beefy connection right there. Now it would be great if everything worked all the time. And I'm not just talking about fiber here, right? I'm talking about fiber and copper. But it doesn't. If I'm running copper, I've got noise. If I'm running fiber, I have the potential for a broken cable, because it is extremely delicate. We talked about our noise being called EMI, electromagnetic interference. And that's just not from other data cables. That's from electrical conduits for affecting copper. It could be a strong radio frequency hitting it, right? I've seen radar cause some weird stuff on these things. So how do we fix it? Well, there's a couple ways we can boost our signals, right? One way is through an amplifier. So if I've got my signal, let's go ahead and clear this. And here's my signal going across, let's say a piece of copper. And it's getting down, I'm approaching my 100 meters, and I plug it into something, right? something, let's say, like a device called a repeater, it would boost the signal, and I'd be good again for another 100 meters. Repeaters were commonly used back in the 90s, right? And originally they were very simple devices. Now, repeaters are layer 1 devices. We'll talk more about this later on, but these are purely a physical device. You plug it into the wall, that's its power outlet. Looks like it got run over with a chair, but it's a power outlet. And it's simply an amplifier. It's just transistors doing this job, right? Weak signal comes in, gets power from the wall, then gives you a boosted copy of that exact same signal. That is one way of doing it. There's their version of it. I like mine way better. Okay, other things that can affect us going across our cable. Latency. If you ever played like a first-person shooter across a really bad internet connection, or maybe across satellite, then you know exactly what this is about. It's how long it takes for the signal to get from one end of the cable to the other. We want our network latency to be as low as possible. Now, when you cross the WAN, when you go into the internet, you're going to start getting into latencies of milliseconds, right? Internally, in our own environments, though, we should have latencies of less than a millisecond. If I see anything inside of my environment that's greater than that, then I've got a problem. There's something causing some issues here. It could be I have an invalid cable length. Maybe I ran my Cat5 too long. I might have a network device that's starting to go bad on me, right? Switches sometimes start fluttering, and they start when they have this piece of logic in them called an ASIC that, like everything else, eventually fails. And when it does, it can start introducing all kinds of noise on the network, which causes Ethernet to have to do retransmissions, which slows everything down. So latency, internal environments should be less than 1 millisecond. Tools I use. I got a bunch of tools that help me troubleshoot my fiber and my copper also. One of the most useful ones actually is called a toner. What this does, it helps me identify my cables. Remember last week when we looked at that picture of the bad cabling environment, and it looked like giant spiders laid this nest of this web of cables in a data center? A lot of places look like that. Good luck trying to trace a cable from one side all the way to the other. You're not going to be able to. And a lot of cables run inside walls. They go inside conduits. They'll go from a wiring closet to a server room or something. Ideally, these cables should be labeled, and they should have been labeled when they were installed. Well, that's a perfect world. A lot of times labeling doesn't get done, and it's up to you, the hapless administrator, to figure out what cable is which. A tool that you have for this is called a toner, right? So if this is my cable, let's say out here in cubicle land, and I want to identify it in the rat's nest that's in my wiring closet, I put a tone generator on it, and then I have this little tone locator. And it's a little wand. And as it approaches the cable where the tone generator is sending its signal on, it'll start beeping at me. Right? And it's like a bloodhound for finding a network cable. Once I've found it, I can label it, and I know what I'm dealing with. I could also use your old-fashioned multimeter. These are just your regular meters that electricians and other technicians use for measuring voltage, current, the presence of a current in a wire, impedance, whatever. They're not as useful as you might think in the network world, but they can do a lot of things for me. They can especially tell me if my copper is connected. Right? Let's see if I have connection all the way through. It'll test me for open circuits. A better tool for that is going to be something like a continuity tester. Right? And what this does, it acts a lot like the toner does. I got to link the cable somewhere. I don't know if this cable is good. So I plug one end of the cable tester onto one side of the cable, the other into the other, and if I have continuity, and it's kind of hard to tell with the picture right here, but there's a little light that represents the wires, each of the pairs inside there, and it'll basically tell me if all the wires are good. If they're not, it's kind of nice to know it. I might also use something called a TDR, right? A time domain reflectometer. Isn't that a fancy name? A lot of our cable runs are long, right? We can go up to 385 feet on copper. And a lot of this is inside the wall. So I don't know what's going on inside that wall. We might have a situation where you got two rooms connected by a piece of copper, and all of a sudden they stop talking to each other, right? They're not able to communicate. Oh, great, what's going on here? I might have a bad cable. Somebody might have cut my cable, which has actually happened to me several times. I don't know where. I've got 385 feet of cable to try to dig through. What a TDR does, it's like a little sonar device. I plug it into the end of the cable that I'm standing at, and it'll send this signal through the wire all the way up to the point where the wire stops, right? So if it's been cut somewhere, it'll hit that termination point and bounce back, right? Just like a radar ping or a sonar ping. When it comes back, the amount of time it took to make the trip, the TDR can tell me how far down the wire my break is. So I might turn that on, hit it, and it'll say, okay, you've got a wire break 92 feet that way. Now I know where to go to find my problem. OTDR, same idea, except it's for fiber optics, right? It's an optical TDR. Instead of sending a electrical signal down the wire, it's sending a beam of light. Same thing. It gets bounced back off the other side, and it tells you how long it took, tells you how far away your break is. It can also tell you things like bad connectors, bad splices, all that kind of stuff. A lot of our devices will look like this, right? These are various cable testers, and don't be fooled by these. These are little PCs, right? They're little computers, and this one here, this Fluke device, it would be very, very capable. It can tell me all kinds of stuff about my wiring, right? Resistance, everything else. Now, the cost on this is starting to ramp up. TDRs and OTDRs especially are pricey. But having these tools can make your life as a network admin, especially if you're responsible for the cabling part of the infrastructure, way, way easier. And that concludes our discussion of structured cabling. As always, please feel free to reach out to me if you have any questions. And I'll see you next week.